The recording is on.
To the SPE Port Harcourt section practical hands-on Python course on the topic automating reservoir engineering and geosciences with Python. My name is Ichiro Kofi, and I'll be running you through a brief course introduction before we get into the course for today. Next slide.
Oh.
All right, so this is the course outline, and for today we'll be going through oil material balance with PyReservoir. Next slide. But participation in this course is still free, but to qualify for a certificate, to get a certificate, you will need to pay $5, and the link for this certificate will be released at the end of this course. Next slide. And to qualify for a certificate, you must have scored above at least 70% in all 3 project assignments. You must have code unique to you. That is, you shouldn't copy code from any other person. Your equations, your formulas should be unique to only you. Your assignment will be submitted via Google Classroom. You'll be required to upload your assignment in PDF format as a presentation containing screenshots of your app and the formulas you intend to use in your app, as well as your code, your Python scripts and code in a .py format. The deadline for submission is midnight of the following day, although this deadline is subject to changes as the course continues. Next slide. Alright, so the courses will be delivered via Zoom and sometimes on our YouTube live. We also have WhatsApp and Telegram groups for this course. Are you sure to join one of them for better communication? Next slide. These are our facilitators for the course. My instructors all the way to our section chairs and part of the volunteering team. Right, so tips for preparation. We have time, clear your schedule, following within this date, and set aside at least 2 hours to work on exercises. Prepare sufficient mobile data to assist you during the streaming of this course. Join the courses early so you can follow up and comment with the instructors as they comment. Get a good system with at least 4 gigabytes RAM. Use a good network service provider. Minimum of 4G network is recommended. Prepare for power in case your system needs to be charged often. Collaborate with others. Ask reasonable questions for clarification. So that's all for the briefing. And at this point, I would like to hand over to Johannes, our coordinator for today, to take it up from here.
Okay, Toro Coffee, thanks for your introduction. Okay, hey everyone.
Johannes,
welcome to our fourth. You hear my voice?
Yes, we can.
Yes, I did.
Yeah, okay. Okay, thanks, Itaro. Thanks for your introduction. So welcome all for this fourth session on material balance analysis with Python. Actually, the title is Material Balance Analysis with PyReservoir, and PyReservoir is a package that yesterday we are talking about formation evaluation. That's one of the packages that I have been developing. And PyReservoir is a Python package or library that can handle not only material balance and but also well test analysis. And if you are already aware with our curriculum, next week we'll talk about using Python for well test analysis, and we'll use PyReservoir also for this purpose. But now I would like to introduce you to material balance. Well, I think some of the participants are not all from petroleum engineers. So I will briefly, very briefly introduce you to what material balance is. And you have ever followed next last week when Destiny taught us about material balance. So it is a lot of equations that reservoir engineers have to be capable of analyzing the reservoirs from the equations. But right now, I would like to introduce just the practical side of material balance. Okay, so I think I will start sharing my screen right now. Okay, there you go. And I will present this slide. There are lots of controls here from Zoom. Okay, okay then. Let's wait for the full screen. It's still loading here, but I think it's a bit lag using Google Slides rather than PowerPoint. So and the okay, let's wait for. There you go. I will share my screen again. Okay, there you go. Okay, for the first introduction to material balance, well, material balance is a tool that reservoir engineers are using to analyze the reservoir. There are lots of things that we can analyze from the reservoirs, like we would like to know what is the original hydrocarbon in place, like oil in place and gas in place. Geologist or myself, I was a geophysicist. We are analyzing the OIP and the OGIP using what is called a static method. So we are using volumetric method to analyze the OIP from the contours, from the structural information that we have from the well logs. We already talked about well logs yesterday. So well logs, if we correlate all the well logs, we can get the information about the OOIP. But in certain cases, a reservoir is not volumetric. It has lots of external drives that that causes the hydrocarbon to be produced. This is called the drives of the reservoir. So here in this slide, the purpose of material balance is the first one to identify the drive of the reservoir. If our reservoir is water driven or it is volumetric, so volumetric is a purely because of the expansion of gas. Maybe you have ever heard about expansion of gas, expansion of oil. It is purely because of the reservoir fluids. But in some cases, maybe reservoir is also water driven. So there are lots of waters coming out from the aquifer and invert that the oil will be produced and it will increase the recovery rate. And also talk about reservoirs, there are lots of reservoirs, and Destiny had told us about the different kinds of reservoirs, and we have to know what is called as the PVT properties. PVT is translation, I think so. And the PVT give us the understanding of the nature of our reservoir. What is the reservoir fluid? What is the fluid in our reservoir, which is the dry gas, or is it the gas condensate reservoir, or is it undersaturated oil or saturated oil? And each of these reservoirs we will discuss and we will analyze using the real data set using PyReservoir. So the next slide is, I want to show you what kind of drives in the reservoir. So it seems that there are lots of drives in the reservoir. Okay, so I've already seen my screen right now. So there are lots of drives in our reservoir. The first one is water drive that I before told you, compression of the reservoir, because rock is not as a solid object, it can be compressed. So when the that happens, as the pressure drops, the pumping for volume and the shrinking of the volume. And also, we are talking about internal drives. Internal drives are the drives that are driven by its own reservoir fluid. If we are talking about a gas, it's because of the gas expansion. If we are talking about oil reservoir, it's because of the oil reservoir. But also, if you are seeing microscopically the oil inside the reservoir, you will see not only oil but also gas phase. So oil is actually not one phase, but it's two phase. There is oil and then there is a dissolved gas. And then this dissolved gas also expands and it will drive the oil to the production well. So I hope that you understand this concept, because it is quite important to know and to simplify this concept into an understanding. And also, we can also inject water and inject gas. It is also what I prefer to call the artificial external drives. Is artificially made by human, but it's external because the reservoir fluid um, uh, um, doesn't cause the drives. So the next slide is, this is the package that we want to use. Maybe you can visit this link, this one. So I have lots of repositories that you can visit here, whether you want to use it for reservoir engineering or reservoir simulation or geophysics. I've also have lots of repositories here. Maybe you want to visit. And one of the repositories that I have is PyReservoir. So on the top right here, you can see this is the repositories for you. If you want to open it, you can learn lots of stuff here. There are lots of codes that you can use, for example, for PVT or for well test analysis or volumetric mapping. Lots of things you can see inside this repository. But right now, I want to show you the package that we will use here. It's called the PyReservoir, and this GitHub is for the purpose of conducting reservoir analysis. You can see here there are 5 functionalities that I have built in my repository here, and one of them is the material balance. Yeah, okay, so if you go here, the MBAL. Okay, so MBAL is a library for conducting material balance analysis, and next we will use well test here. So the well test, this library, you will find the libraries to compute the OIP and to produce the natural balance plots, and also to using widely used methods. Okay, so this one is our this will be our toolkit to conduct material balance analysis. Okay, so I think it's right now for the real hands-on programming. As yesterday, I also share a link where you can also go inside this link. Okay, so bit.ly Python MBAL, you just go into this link. Okay, I think I can do this. Okay, git.ly. I have to put it in manually. Python.ml here. You will find the notebook that we will inside here. We will code. We will create a code using PyReservoir. Okay, I think it's time to turn off my video because I think it will be better to work with like this, so the video won't be like as. Okay, okay, here. Um, this will be our notebook. And inside this notebook, you can see here the content of this notebook. These are the things that we want to do today. The first one is teach you how to do a linear regression, because regression is the fundamental skill to do material balance. And material balance plots, if we want to calculate OOIP or OGIP, okay, we just plot all the data from the production data, and then we devise a specific plot, and on the specific plot we do the linear regression or the curve fitting. So before we are going to our analysis, we will do the intro to regression, and after the intro we will go directly to the application. We will create a code to make material balance plots for one is for dry gas. Dry gas is our first type of the reservoir, and the second type is gas condensate, and then saturated non-volatile, because it's quite lots of terminologies that we use here: volatile, saturated. Each when we are touching with one of these reservoirs, we will briefly. I have a slide that explain to you briefly about. Yesterday, we can copy this notebook to our drive, and then with our drive we can do our coding here. Just wait for a second here. Okay, so before we are moving on, if you have any question, you can ask. Is there any question before we are continuing from the participants?
Not yet. Just move on.
Okay.
Okay. So someone says, can you use Python for history matching? Can you use Python for history matching?
Yeah. We can do anything with Python. I mean, when you are asking, can we do something with Python? My answer is we can do that with Python, but it is not so easy to give the output in a very short time. We have to understand the algorithm. We have to understand the model, and then we build the codes. And anything is possible with Python. We can do anything with Python. And maybe if we have any time left after this session, in this repository that I have shown you before, the PyReservoir repository, you can find my codes to do the history matching with Python. They are using, for example, machine learning we can do machine learning for history matching from the history from the production data. So it is either climate matching or the new term of machine learning or data analytics. It's possible with Python. So everything is possible with Python. Okay. I think that will be a really interesting discussion. Okay, so we can have the discussion in other time, but I'm really interested to discuss about that. Okay, right now we are seeing the notebook, and for the first time we import these libraries. We have NumPy, Matplotlib, and Pandas, and this is actually, I prefer to use just these libraries and craft lots of codes that that comes from this. We can do anything from this three libraries with these libraries. So you have to be creative on creating something from this only three libraries. Okay, so I will guide you one by one, so you will understand how to do this and that with Python. Okay, I think this all have already been installed. Imported. So we don't have to be. You don't have to install these libraries. And the next cell is to clone the GitHub repository. So this one is a PyReservoir GitHub repository. If you are aware, yesterday we are using formation evaluation, and today we are using PyReservoir. And for next week, when we are talking about well test, we will also use this PyReservoir. So this code will be the similar code that we will use next week. And then here we have to import the system. I think it's a quite complicated to understand this, but it is like this: when you have cloned a repository, when you will put it in a directory, so that when you make maybe you are using software, you can locate the file in a certain directory. Okay, so the way we are using the import system and sys.path.append, it is just very similar to what we do when we are using softwares or when we are coding with MATLAB or other programming languages. Maybe you have already programmed with other programming languages. Okay, so after this, you can see all the contents of this repository in this tab. Okay, so here you will see the contents. This one is the data that we are going to use here. So if you expand this this tab, it will show us all the data. Okay, this one is a data. Okay, all of this data is production data. Okay, and also you can also want to use. Okay, this one is MBAL, and these three functions that we will use right now. Okay, so it seems that all the functions and data have already been inside our Colab. So the next thing is, like we just did yesterday, we import these functions. The way we import is we are using from MBAL import dry gas condensate, and the last one is oil. Why I'm typing like this? If you are clicking here the MBAL here, okay, you are clicking the file, you will see the source code. Okay, and inside the source code there are three functions. And each function corresponds to each type of the reservoir that we want to analyze. So for example, if we want to analyze dry gas reservoir, we are using this function. And maybe we want to analyze oil reservoir, whether it is undersaturated or saturated, both of them, we are using oil function. Okay, so you can find all of the codes here. This one is the codes that I built for these packages, so you can see. Okay, and the next thing is I want to show you how to do the linear regression from scratch. Okay, so the specific library that we want to use is SciPy. SciPy is also another important libraries other than NumPy, Matplotlib, and Pandas. You will also find lots of libraries like Keras, TensorFlow, that's for the machine learning, and SciPy is for the scientific computing. Um, if we are analyzing Fourier transform or some tough like signal analysis, we are using SciPy to do that. And here we use SciPy to do linear regression. And this SciPy.optimize import curvefit. Okay, and then we will make dummy data for ourselves. Like I want to do like this. The X array, well, we have already know how to do that to produce an array from 0 to 50 into 100 numbers. Okay, if you print all of the numbers, okay, without this bracket. Okay, so you will see all of the results here. I have already sent you another notebook yesterday, 2 notebooks. The first one is the intro to Python, and the next one is the formation evaluation notebook. And if you want to study this, the basic things of the Python, you can go to the first notebook that I have shared in the WhatsApp group. And here, okay. Okay. So we want to create a function. Okay. So the way we are creating a function, we use def, and the name of function I want to say it as linear x, a, b. So because of this function, we'll have the form of a times x b. Okay. So we will type this as a times x plus b, and this function will return us the y. Okay. So the structure of making a function is you are starting from def, and then you are stating the name of your function and also your input, and then the formula, and it must be closed by the variable, like what will your function return. Actually, there are also functions that doesn't have to be, we don't have to put the return. So, but here I want to show you that return is quite important when you make a function. Okay, so we have already made a function, and then okay, so here we want to create a dummy data. We have already get a dummy data here. Okay, this one is the dummy data, and I want to make a dummy data, so I will make a set of data. Let's call it y. Okay, we use the function. Okay, and before we are using the function, we define the parameters. Here I want to use a as 0.5 and b as 1. Okay, and if we print y, it will print us the result of this function. Okay. So this set of data, the X and Y. So we imagine that we have this data, and then we want to do linear regression. And of course, I want to add some noises here to the Y. Okay, so I can do this using numpy random.random. You can also find this code in the notebook that I have shared you yesterday. The notebook of very brief intro to Python. Numpy random, because we are generating 50 numbers here. So we try to be consistent. We will use also 50 numbers. And if we print the noise, it will print us all the random numbers from 0 to 1. Okay, and then from this data, okay, from this data, I will plot first. Okay, so plt.show, it will show us the data. But here, as you can see, so you can also type like this. This is for changing the style. Okay, sorry for this one. Okay, this one is before we apply the noise. If we want to apply the noise, we just add the Y to the noise, and it will print. It will show us. Okay, I think we have made a mistake because we are generating like how many this X, how many numbers that I have before. It's okay, so 100. So because I have generated 100 numbers for X, so the noise should be also 100. And you will see here, the data has already been, it's not crooked because we don't use noise. And after this, we have noise. So from this data, we want to do the linear regression, okay? And the way we are doing the linear regression, we do like this, POPT, because we are using the curve fit function from the SciPy to fit our data. The first input is the name of the function, linear, and our data, okay? Our data is X and Y. So if we print the POPT, okay, this code will calculate the most appropriate A and B. Okay, A and B is our parameters. You know, A times X plus B. So linear regression will produce A and B. And POPT here, the first one is A and the second one is B. So we can define A comma B is POPT, and it will print us what is A and what is B. Okay. So B here, we have the result A equals 0.5. It is very near to our parameter. We define here as 0.5, and it returns us 0.5, okay? And also B. But you see here, interestingly, the B equals 1.6 is not so near with our defined parameter. I want to ask you why we are getting this result. Maybe some of you want to type your comment, your answer in the comment, or okay. Maybe Destiny, if you want to organize one of the maybe participants, if they have answer, they can also give an answer for this. Why? After I did the linear regression, it is 1.6. It is different from my first parameter here.
Okay.
A equals 1.
Okay.
Yeah. So is there any participants that have already get the answer for this?
None yet. I've not seen any chat.
Okay. Okay. So it's because we have added noise to our data. Okay, so because we are adding noise, this one is the noises, right? This one, because if we don't use this, okay, it is before we apply noise. It will return us exactly that B equals 1. But because we are adding noise here, okay, so it will print us the different result. Okay, that's quite interesting. So that's why in data science, we are using what is called as bootstrapping. You can build it in the
Johannes?
internet. Yes, sure. Okay.
Teataraj says, what's noise?
Sorry?
Like, what's the meaning of noise? Teataraj
Okay,
says, what's
so
the meaning of noise?
yeah. I understand the question. Thank you. Noise is like I want to add some impurities. Okay, like yeah, noise. Like I add the noise here. Okay, because as you know that all data is not having like this one. It is not it is the ideal data, okay, but the data from the field or from somewhere that we get, okay, it is not as clean like this data, okay. So the way I did this, I want to show you how data looks in the field or somewhere else that we get from any source that we get the data. It is not clean, okay. So and linear regression uh, um, the objective of linear regression, we want to find the linear relationship between variables. Okay, so if we plot this data, okay, this one is our data. This one is our data, okay, and then we plot. Okay, so next thing I want to plot the result of the linear regression. Okay, so you can do like this. A times x, okay, so because we have already had the x plus b. A and b are the parameters that we have already obtained from the linear regression. Okay, so if we plot the regression line, the x and y regression, we will see the regression line. Okay, maybe I can adjust this alpha equals 0.5 to make the dots looks more dimmer with this. Okay, 0.5 or 0.6. 0.5 will be fine. And I want to colorize the line as color red. Okay, this is our result of regression. And it is exactly what we are doing in material balance. So in material balance, like this one, the slope can mean your OOIP or original oil in place. And the intercept can also mean the OOIP. So why I'm showing this, it is the basic of material balance, okay? So I hope that you have already understand the concept because it's quite important before it's more complicated that we think it before. Okay, so I want to go back to my slide to show you our first type of our reservoir. It is called the dry gas reservoir. What is a dry gas reservoir? It is a reservoir that produces only gas without any liquid. And why is there why the reservoir have to produce liquids? It is the properties of any reservoir fluids. When you increase the temperature or decrease the temperature, or you maybe decrease the pressure or increase the pressure, you will change the phase from, for example, from liquid to gas or gas to liquid. Okay, so for this type of reservoir, dry gas reservoir, because the production tends to reduce the pressure, because there will be the pressure reduced because of the production, the phase of the reservoir fluid will change. Okay, but in this case, the gas inside the reservoir, when the pressure drops, it will remain as gas and it won't drop any liquid. So that's why in this dry gas reservoir, we only get dry gas without any liquids. The next one, we will talk about the gas condensate reservoir. So gas condensate reservoir is a reservoir that not only produce gas, but also liquid, okay? Because the gas condenses into a liquid. I hope that you have already understand this concept. And the dry gas reservoir, it is driven purely by gas expansion, because there is no liquid. The liquid cannot cannot drive the reservoir. Yeah, because there's no liquid, there is no drive from the liquid. And also, interestingly, we have a recovery factor is relatively high, because it is purely because of the gas expands. If you see you are blowing a balloon, okay, it is quite fast to fill the balloon with the air. So because why the balloon is expanding is because of the expansion of gas, and the expansion of gas is the most effective drive in the reservoir. Okay, and there are 5 plots that we use here. We are using plots when we are analyzing material balance. There are 5 plots here. Okay, the first plot is the plot of F versus EG. I think you still remember the last week lecture about the material balance. So these are the variables in material balance. Okay, F is reservoir voidage. You can maybe after this session I will share you a nice PDF or handout that explains these variables in a really simple way. Okay, it is not theoretical. We don't have to care about the theory. We only have to know the simple meaning of all of these variables. Okay, so for this first variable, first plot, if we plot this one, if we do the linear regression, we will get the slope, and the slope is GFGI. GFGI is the original gas in place. Okay, so if we plot also the second plot here, this is the P per Z plot. It is quite often we encounter this in the industry. Okay, the intercept of this is the oil and OGIP. Okay, original gas in place. And this plot, okay, this plot is it also gives us the slope as the GFGI, and this one the intercept as GFGI, and we have this spatial plot here. Okay, so this plot will tell us whether or not our reservoir is water driven. If we are seeing this plot as the straight line, okay, horizontal line, it means that our reservoir is not water driven. If it is something like this, okay, it has a slope, it will tell us that the reservoir is water driven. Okay, and we will use this concept for our programming now. Okay, we are going back to our notebook. This one is our production data. Okay, you can find this production data here. Okay, dry gas with water drive, and the one that we can load the production, we are using pandas. Data PD with CSV, like we were doing this for the formation tops yesterday. Read CSV and give the file path, and we are showing the production data frame. Okay, I hope that the kernel is okay. Okay, that's amazing. Okay, so we are seeing here the production data. The T is the time, pressure. GP is the gas production, the oil production. So besides gas, the company also produces the oil. Okay. And this one is the total gas production, water production. Bg is the gas formation volume factor. It is also it is another term that you need to know. Bg is the gas formation factor, and Bw is the water formation factor, and Z is the compressibility factor. Okay, we have this data. Okay, and then it is quite interesting in this part. Okay, so I want to visualize the reservoir pressure, oil production, and the cumulative gas production into one plot. Okay, so first of all, we define the variables data. What is the name of the column for data for time? It's T. Okay, so every time we define our variables, we have to look at the column name. Okay. So P is data, P values, GP data, GP values, and P is data, data, and P values. Okay. So if we show the oil production, this one is the data. Okay. Next thing is the plotting. Okay. First thing, you have to add this plt.figure. Okay. Figure fixed size. I will explain this after this. I want to make a plot that has this size. Okay. So if I use this plt.show, okay, so every time you are plotting, you have to add this plt.show. Nevertheless, you don't do this in, for example, PyCharm, it won't print any plot, okay? And then we type this host fig add subplot S111. Okay, so here we already have the template for our plot. Okay, and okay, so you just follow this, and you will understand what is actually what I want to do. So I want to make a plot. Okay, so maybe I have a doodling. Okay, so there's no. Okay, so I want to explain, but there is no a pen or doodling here. Okay, so that's fine. Okay, so okay, host at okay host sorry host twin x. Okay, so maybe you are confused with this one. So I want to plot all of this data. Okay, so it will plot us all the data. Okay, so this one is for the oil production. Okay, and the next thing is for the GP. The next thing is for the pressure. Okay, so what's wrong with this plot? It is not really comfortable to see this plot because it has the different scale. Okay, so I want to change this plot so that this line have the same proportion. Okay, so you will understand after I show the codes. Okay, so you just follow these codes. Part 2, host twin x. Okay, and then host plot. So we will plot first the pressure, okay, but using this style. So host, par1, par2, each represents the plot. So for host, I want to plot the pressure, par1 for the GP and par2 for the gas production. Par1 dot plot dot T and P, same. Par2 dot plot T GP. All right, okay. So okay, so you recognize the difference between these plots. Okay, so maybe I want to show you the color. I want to show it as red, colors black, and color is green. I want to, this is a blue or blue, I think. Okay, is there any difference with this plot and this plot? Okay, it looks better, right? Why it looks better? Because this line has the same proportion. Okay, now they have it doesn't have the same proportion. It should be like this one, the green one is the pressure. Okay, but you can see the decrease or the reduce of pressure because it is, as you can see, the y-axis. Okay, and our pressure is, this one is only 7,000, but this one is 500,000, even 500,000. So we cannot see the decrease. But if we do like this, we will see all the decrease and all the increase. Okay, and then I want to because it is now stacked. I want to separate this one as points right set position, yeah, position. Okay, outward. How many? I want to show you. Okay, 80. You will see now the scale have been separated. Okay, for the first scale set.x label. So for the y label, it is pressure, PSI, in the unit of PSI. PSI for the host, sorry, for the par1 set Y label, cumulative oil production, production, okay, par2, that set Y label, cumulative gas production, SCF. Okay, it will all print the labels, and the another label is the X label. That's set X label. It is the time, date, and then maybe host set title, production history with size and pet. Okay. Okay, this one is our plot. Okay, it looks better, right? Or maybe I want to restrict this to 0. Okay, so I can do this. Host, okay, host. We set the limit xlim from minimum value of t and maximum value of t. It will adjust the scale from the first beginning to the end of the production. Okay, so this is the visualization of the production data. If we are using this plot, I believe that the industry will be really mad at us because it doesn't tell anything about the production history. If we are showing like this, okay, it is really clear to see how the pressure declines and the production increases as the production proceeds. Okay, now we will go to material balance analysis. And the dry gas material balance, we will use the function that is called dry gas. So first of all, we use help to find out what the inputs that we want to use. Okay, so we will use this dry gas to conduct material balance analysis. This one is the inputs, okay, and this one is the outputs. And the step of doing material balance analysis, we are using first this function. After we have used, we get the outputs. We do the second function, the plotting, and the output will be all the plots. Okay. So first of all, like we just did yesterday, we can copy and each of these inputs.
Hello, Johannes.
Yes, Destiny.
Quick one. Someone says, why can't we use min functions for capping x or y axis? And
okay.
and
yeah,
that's it. And someone says, why do we have to use twin x? Yeah, of course we can. You can add legends.
Okay. I think the question is, sure, definitely, It's like we want to show like only from 7,400 to host. So one xlim is for x-axis, right? And this host set y-lim, okay, from this one to this value, okay? Yeah, so we can restrict this. You just have to adjust this this line. You define the y-lim and you define the minimum value and the maximum value. Okay, so I think there is we can increase our okay. So I think it's clear, Destiny, right? Is there any questions like the visualization things?
Okay, none. Just go on.
Or we just continue? Okay. Okay, so now we are defining our values, okay? So GP data, okay? GP values, CF data. Okay, I want to explain here. We have this data, okay? We have this data. And also, we need to know other variables like the compressibility of the formation, the compressibility of the water, and the porosity, and the initial water saturation. Okay, I have already listed here all the variables. We have the formation compressibility as 3.5, water compressibility 2.9, and the SVI as this number. And one note here, we have the data, but sometimes when we obtain the data from the field, it is recorded in different units. Like maybe we use cubic meter, not barrel, although barrel is the field unit, so we need to convert the data if it has different units. In this case, our data, it has different, like it is not already in field units. We have the SCF, okay? So I guess you know what this unit is, okay? So mm is 0.6 standard cubic feet of gas, SCF is the unit field unit of gas, okay? And the gas SPF, FEF, sorry, is this, okay? So for this two variables, we have to convert it first, okay? So which one? This one is the cumulative gas production, so it's GP, okay? GP, I want to convert the unit from to SCF. So we 1.6, okay, and also BG, we want to convert the unit from reservoir barrel over MSCF to reservoir barrel over SCF. Okay, so reservoir barrel is the field unit for oil. SCF is the field unit for gas. RB is the reservoir barrel. Why reservoir barrel and why standard like there is RB and STB? RB is the unit of volume as recorded in the reservoir, and STB, okay, there are two, STB and RB. RB is for the reservoir, okay, and STB or standard barrel is the unit when we record at the surface. If you have already understand what is the formation volume factor, if you have, for example, gas in the surface, the volume will be different if you go in the reservoir, okay? It will expand, okay? So for oil, if we have the oil, for example, 2 gallon of oil, okay, and then you bring it into the subsurface, into the reservoir, you will have only 1 gallon because it shrinks. So if you want to be rich, okay, you cannot go to the reservoir because you will lose your quantity. Okay, so at the surface, the oil, the volume of oil will be higher than we have in the reservoir. So here, Bg is the gas formation volume factor that I told just right now. So volume factor is the quantity that defines how much the fluid will shrink or expand when we go to the reservoir. Okay, so here I want to convert from RB MSCF to SCF. So okay, so like this, right? MSCF is 1000 SCF. Okay, so this one, okay. And then we have the CF. CF is a formation compressibility. Here is 3.5. The water compressibility as 2.9, and the initial water saturation as 0.21. And here you see the unit is microsip. Microsip is times, so it's the order of 6. Okay, so okay, I think it's microsip, 1 microsip.
Johannes,
I want to put it as a comment. Yes, sure. Destiny.
Someone says you wrote min T. Can we also write min 0?
Oh, this one. Hello. So this one. So what do you refer? 0?
Yes.
Destiny?
So
I cannot understand the question.
Yes,
okay, he's like, can you use min 0? Can he use min 0 instead of min T?
For what part? Are we referring to this?
Just scroll back.
So this
scroll
one.
up. I think your screen is not moving. Your screen isn't moving. Seems your screen is.
Yeah, which one? Which one are you referring right now? It is. So Could you confirm him which part that he's actually asking? Because I don't quite understand what is the min t or min 0. Okay, I think I get from Tirtha Raj.
It's okay, I'll chat him up.
Oh, okay. So you understand the question? Because I don't understand it. I think it is he's referring to this plot, right? Okay. Yeah, we can change this. I'm sorry if I don't quite understand your question. Maybe you can ask me directly for your particular question, but we will move on here right now. I just hope that all of you understand. If you have any question, kindly just kindly please ask. Okay, so we can maybe you feel that the explanations are faster, or I have to explain this term or anything, you can just kindly ask. You can kindly ask in the chat box. Okay, so now, okay, so 1 microsip is, okay, 10.6 psi. Okay, okay, okay. So for most people will understand this. Okay, so this is the unit for the compressibility. Okay, so for this for this exponent we use this. Okay. And then for this also. Okay, so after we print the variables, okay, and then we calculate the params. Okay, so so you see here in this help. Okay, there are two functions. The output is this. So we put this function. Okay, equals calculate params. Calculate params is our function, and then we put all the function here. Okay, so first of all, I need to explain you first of all. Okay, this function you have to type like this. First you type the type of your reservoir, dry gas. Okay, and then for this type of the reservoir, okay, we are back to our code. Okay, type this X, okay, and dry gas. All the inputs, okay, here, okay, okay. So okay, so there is dry gas now attribute. Okay, there is a mistake here. Calculate params. Okay, so we are done with the second step, and then after we are having this, before I already explained to you these plots, right? Okay, so these variables are computed or calculated using this function. So this one is the output, and then with these variables, we will plot this one as y-axis and this one as the x-axis. Okay, so we put the x.plot. Plot is our function, and we put all the inputs here. So we just wait for a couple of seconds. Okay, z is not defined. Why is not defined? Because this function also needs another input. Z. And because we don't define it, we have to define it. Okay, Z is this are inside this production data. Okay, so we are calling the Z like we did with also with the P pressure Z values, and we run this code once again. You will get the plots here. But because these plots, I want to expand the plots so it will be visible, fixed size, okay, 10.12. So it will control the size of the plots. And you will see the plots, the material balance plots, okay. Here are our material balance plots, okay. And in this plot, you can see the results of the initial hydrocarbon in place. The first result you are seeing here is the free oil in place. So it is logical here for all the plots we have 0 because it is dry gas. So there is no oil inside our reservoir. But later when we touch to the material balance for the gas condensate reservoir, okay, you will see that the NFOI or the free oil gas in place is not 0. Okay, GFGI is the free gas in place, OOIP and OGIP. You understand that? And this plot tells us all the information, the OOIP. And this one, just pay attention to this third plot. It is the water drive diagnostic plot, okay? So the key thing is if you are seeing, so first we see here, okay? So for this plot, if it is horizontal, it means that there is no water drive. But what we are having this here, it is not horizontal. So it means that the reservoir is water driven. So only from this plot, we can generate some information from our reservoir. And which plot that we have to trust. If you see here, the GFGI, you compare with the other plots, it is quite near, okay? Here is about 900 TSCF and this, okay? So you can compare it yourself, okay? How close are these values? But you cannot use the third plot because it won't tell you anything about the OIP. It just tells you whether your reservoir is water driven or just volumetric. Okay. So next thing, we want to proceed to our second type of reservoir, which is the gas condensate reservoir. As we have already discussed, gas condensate reservoir, it is not a dry gas. We also have the condensate or the liquid inside the gas. So beside we have the OGIP, we also have the OOIP because there is a liquid phase in our reservoir. So there is a called it is not oil actually, it is the condensate. As the gas condensates, it will form into a liquid. And this one are the plots that we use for the material balance in this type of reservoir. There are only 4 plots here, okay? So we will use this plot. We are going back to our notebook here. So we go to the second reservoir type, okay? So this one is our second data, okay? It is from Bacon Lime from the US. And then we just repeat all the codes, okay? We just repeat it, okay? So data equals pandas with CSV file path. Okay, and then data. It will print the data. Okay, this one is the data. Okay, and then also for this reservoir there are variables. Okay, so for example, the formation and water compressibility is 0. It means that the formation and water is incompressible. Okay, and also this reservoir has this property 0.2 initial water saturation, and it has the dew point pressure. The dew point pressure, maybe you have understand, the dew point pressure is the pressure when the gas condensates into a liquid, okay? So above this dew point pressure, the reservoir will stay as a dry gas reservoir. It means there is no condensate, but as the pressure drops below this pressure, it will form the condensate. So if you are seeing this data, all the pressures here are below the dew point pressure. So it means that at this pressure, the reservoir changes, some of the gas changes into liquid, or we call as condensate. Okay, and there is another no gas injection. So just imagine that the company doesn't do gas injection, so there is no gas injection for the reservoir. Actually, there will be a longer discussion why gas injection is important for the reservoir. But for now, we just follow along that this reservoir there is no gas injection. Okay, so and then some of these variables are not in field unit. So it means you just guess yourself. We have to these variables to the field unit. All right. Okay. So we are using another function here. We use the gas condensate. Okay. So we type help to find out what inputs are required. So these are the inputs. So as you can see here, this is our additional inputs, the dew point, okay? And other input like GI is the gas injection. So if you have gas injection, you will have the data, okay? So because this data that doesn't have gas injection, so we will leave GI as zeros. And then after we calculate the parameters, we get the output. And from the output, we do the plotting. And from the plotting, we will see these plots for our analysis. Okay, so we define all the inputs here. Okay. And okay, so I will explain new variable is called the RV. Okay. So R call it as the reservoir that produces. If you study something, it is really interesting to see like the reservoir fluid is really unique. Okay. So first of all, you have the oil. Okay. Inside the oil, you also have the dissolved gas. So you won't see like just oil. You also see the other phases, like you will find the gas inside the oil. Okay, and inside the gas, you also has the liquid. So there are three phases actually: the oil, the gas, the dissolved gas, and this dissolved liquid inside the gas. So gas condensate reservoir is unique because you have these three phases inside the reservoir. So for this type of reservoir, it has special variable, which is RV. It is actually not special because RV is also for other reservoirs. But RV indicates that our reservoir is gas condensate, or also what we will call it later as the saturated oil. Okay, so okay, P and values. Okay, data. Sorry, P due we define as K1, BG data, BG dot values, and sorry, this one is not comma. Okay, BO values, NP data, NP values, GP. So we have to repeat these variables. GI values. Okay, so for CF we have 0 because we just declare it doesn't have the formation compressibility, and the 0 too, and our initial water saturation is 0.2. Our RS is we have defined data RS values and data RV dot values. Okay, and also because some of this data is not in field, we have to convert it first, or convert them first. Okay, so BG we have to convert from okay, so from RB, so BG we have times 1 over, okay, for MCF, right? Okay, so for BO BGP, GP is BSCF, so you have to convert it to times B billion is 6, okay, and GI, okay, GI, RV is RV is SDB. Okay, so for this, I have to convert into okay, BSCF is 9, MMECF is 6, and one thing, we don't have the gas injection, right? So we declare it as 0. Actually, we can use this like 0, 0, 0, but it is not efficient to do this. Okay, we use and numpy zeros, learn data. Okay, so with this code, it will print us the GI as 0. Okay, 0 array. Okay, and if we run this code next, okay, so we define the type of our reservoir as gas condensate, and we start to calculate the parameters. Okay, calculate parameter. Okay, so you have to add this X for the parameters. It needs this inputs. Okay, so we have done our calculation with the variables. We have already done to calculate these variables here for our plotting. Okay, and then we just plot all the required inputs. Okay, so you can copy and paste here. Okay, one thing we also forget to define what is Z. Okay, so we haven't defined Z, so we define here Z data Z dot values. Okay. Okay, so these are our plots. Okay, if we expand it just like we have done before with our dry gas, we use the same size. Okay. So here you go. This is our result for the gas condensate reservoir. See, okay. So you will find that this reservoir has the OOIP. Why? Because this reservoir has the condensate. Okay. So, and then you can see here the amount of gas in place. Okay. So it is quite near. You have 2.4 41 and 2.30. Okay. And look again, pay attention to the third plot. As I have explained before, if we are having the horizontal line, okay, it means that our reservoir is not water driven, and it is quite horizontal right now. So it means that our reservoir maybe has a little water drive, but the water drive is quite weak or no water drive. So that's why here we see the line is not horizontal. Okay, so if you compare this with our previous reservoir here, we have a water drive because the third plot shows not horizontal line, but in this plot you will see they're relatively horizontal. Okay. Well, okay, I think I have finished for the two parts, and I will continue with the next one. But maybe I hope is if there is any question for this part. Destiny, so how's the participants? Okay, I think Destiny is not here. It's just entered the waiting room. Okay. Okay, if you have any question, maybe I cannot see in the chat box because I'm using mobile phone here for talking, and I'm using laptop for sharing my screen. So that's why I cannot see your chat box. But um, yeah, but I hope you understand. If you have any question, you can ask me in the WhatsApp or just directly poke me in. How are these graph parameters defined, sir? Okay. Um, Last week, Destiny had taught us on how to calculate all of these variables. Okay, there. I guess Destiny had already shared one slide, and in that slide, we can see all the defined. I mean, if I have longer time than this or separate session, we can discuss the basic material balance, because material balance is not difficult. It is if we understand what is, for example, BG, BO, NP, GP. These are the PVT properties. We are having this BG and BO from the lab experiments, and RS and RVs from the laboratory experiments as well. And this one, CF, the formation compressibility, we have from scale data. Okay, so from scale experiment. Okay, so and then for the water compressibility, also from PVT experiment. SVI here we have from the WELOC. Okay, before we talk about WELOC, we can define the initial water saturation, and all the formation like F is a reservoir wattage, and EFW is the water expansion factor. I have all these formulas. Maybe I can show you later. After this session, I will share a material that defines all of these variables. So maybe if you want to apply this code for your study or for your research, you can find this material and you can follow all of the explanations in those documents. So I will share the documents to you after this session. Okay, so I think we are just moving along because we have a really limited time. We have only 2 hours. Okay, so there is also another reservoir that is called the saturated volatile reservoir. Okay, so to discuss also, okay, so very briefly, what is called as the volatiles and oil PVT. So these variables BG, RS, RV, BO are the PVT properties. Okay, PVT properties are the natural properties of the reservoir fluids. It's like you define what is the density of water, what is the specific gravity of oil. So all of these are called the PVT properties. BG is the gas, FVF. This one is the oil, FVF. RS is the solution gas oil ratio, and RV is the volatile oil gas ratio. So for the volatile oil, the gas dissolved in the oil have the volatiles. Okay, so I have told before that oil is not only one phase, it has 3 phases or 2 phases. Okay, so for the volatile oil, you will see the volatile oil is more lighter than non-volatile oil. So if you see black oil, okay, it corresponds also to this type of oil, okay. And if you have a lighter oil, okay, not heavier one, we have the volatile because we have some maybe some gas and liquids in there. Okay, so after this we are talking about the undersaturated oil reservoir, okay. But because we have a really limited time, I think we will go directly to the fourth reservoir type, okay. So this one is the material balance plots for the undersaturated oil reservoir, and for the saturated oil reservoir we use this plot, okay. So I will send this slide to you, okay. So we will use, okay, so we'll use this data, okay. So going back to our discussion in our notebook, we are right now using a new data from Wolf. Yesterday we also used Wolf data, and right now we again use Wolf data for our analysis. Okay, so Wolf data is really complete. We can use it for anything, but for now, a Wolf field is an undersaturated non-volatile oil reservoir. Okay, this is quite a long term to define this reservoir. Okay, okay, we have the data here. Okay, we have the data in this Wolf directory. Okay, and for this data, we again import this function, this data, and print the data. Okay, so this one is the pressure. Okay, MP, GP, WP, GI. WI is the water injection. So there is no gas injection, but there is a water injection here. Okay, and then the RP. RP is the cumulative oil gas ratio. We won't use this for now. And then BO, BG, RS, and RV. Okay, and from this data, for this full field, I have compiled from the reports, and it has these properties. So the formation compressibility is this one, okay, this microsip. For this number, if you are critical enough, you will see that this formation is more compressible. So before we have 2 microns, but for this formation, we have the formation seemingly very, very compressible. Not very, very, but only one very is enough. So we have already have this data, and this data we don't have to convert, because all of this data has in the unit of field units. Okay, so first of all, I would like to list all the columns. It is not df, sorry, it's data, because we define it as data. Okay, so it prints us all the column names. Okay, and then we input all the required ones. For this type of reservoir, we use the other function that is called the oil function. Okay, so for the oil function, we will first calculate the parameters that we will construct this plot for f and this ones. Okay, after we are getting all the parameters, we don't use the gas cap for now. We use the plot to plot the material balance plots. And this, you have to type what the type of oil reservoir you have, because here the full field is the undersaturated. So you need the undersaturated. Show you after this. So the first one, we input all the required inputs. Okay. So it's just the same like before. We are defining all the variables for our inputs. Okay. Okay. So maybe you ask, what is the difference between undersaturated and saturated? Saturated oil reservoir is all reservoirs that the initial pressure is below the bubble point pressure. Okay. But for this reservoir, because it is undersaturated, it means that the initial pressure, okay, so before the production, we have the initial pressure. We measure the pressure before we are going to production. So we have the initial pressure, and the initial pressure is above the bubble point pressure. Okay, find gas in the free phase. You just have the gas in the dissolve phase. Okay, so for P, you defined the pressure here. And for the BO, okay, this one, that values, okay. Okay, so for BG, okay, RV, data, RV, dot values, okay. So for RS, okay, this one, dot values, data, I think, and okay. So this is it is really easy to use Google Colab because it will automatically do all the inputs, like it knows what we are going to write. Okay, so GP values and GI, we have the GI data, the gas injection data. Okay, that values CF. We have, I think, okay, this one, 4, okay, and for CW we have this one, I think, and for SWY we have, okay, so we have done with all the variable inputs, and next thing, we define again our type of our reservoir. We use this oil, okay. So for gas condensate, you type the gas condensate. For dry gas, you define it as dry gas. Because this is oil reservoir, we use as oil. Okay, so we again copy this outputs and calculate params. Okay, this one is all the inputs I can copy. Okay. Okay. So we have calculated all the parameters for our plotting. So now we just plot our material balance plots. Okay. So oil type we define as undersaturated. Okay. And then F, BTO, we just follow the pop-ups here. Okay, this is really nice to use Google Colab. Okay, BO, RS, RV. Okay, so I hope that you pay attention here. Okay, pay attention to this plot. Okay, very carefully. You will see here, okay, that this line. Well, if we are going back to this, you can conclude the material balance plots are correct if we if data points here. But in this case, you see a pretty anomaly here, okay, within our result. It means that this reservoir is not what we think before, okay. It should be, there should be a water drive in this reservoir, okay. So the next thing we want to do for this plot, so pay attention carefully, it should be this line is the regression line, right? It should be lower than this, so it should be okay in this. Okay. We can actually control the regression point using end. Okay, so if we are adjusting our variable here, such as equals 7, so it will gradually change the line. Okay, so our objective here, it should be lower. Okay, should be lower, and it should be like in line with this 4 points. Okay, so because it is like the 4 points, we define it as 4. Okay, so this is actually our material balance plot for this field. Okay, so it simply explain us that this reservoir is water driven. So that's why before we produce the higher regression line. Okay, so if we are seeing here, okay, so this is our OOIP. Okay, I think I just missed something here. BO. Because the OIP is really small. Okay, I think, oh, this one. Okay, so because the compressibility is in microsip, so we have to add this. Okay, so if we compute the plot, okay, so you will see this. Okay, so this is the correct. Okay, this is the correct oil in place. And interestingly, if you want to compare it with the true report, okay, so it is quite similar. Okay, our result is quite similar to the report, or someone has already done material balance also, and the result is quite near. Okay, so it means that this reservoir is water driven. Okay, if you are seeing this anomaly here, okay, it means that there is an increase in the oil in place. It is because of the water drive. Okay, so for the last 15 minutes, because we have to really finish it in 2 hours. Okay, so for the next 15 minutes, okay, so it will okay, so for this calculation, I want to calculate, because we have already know that this reservoir is water driven. Okay, my next plan is to calculate how much water invade our reservoir. Okay, so, or how big is the water drive. So the way we are computing the aquifer influx, okay, we are going back to the slide. There are but in this, Van Everdingen and Hurst, maybe you have ever heard about that in one of the textbooks. Okay, so for this, we will calculate the aquifer using the VEH method. Okay, so and we will use another function that is called the aquifer. Okay, so this so we have done with the MBAL. We will use the other function, the aquifer. Okay, so from aquifer import. Okay, so if we are seeing this file, this function, I have made a function that can calculate the aquifer influx for different methods. So you will see this is the first method. The second method is the VEH. Okay, so this one is a VEH. And also the third is the Fatkovich. Okay, so right now we will use the VEH. So we will import the VEH, and you can see the help to find out what's the input is required. Okay. Okay, so for this cell, it is actually complicated because, okay, so I have to explain this. These are the dates. Okay, when you are having the production data, we have to convert that the data have to be have to fit with the format from pandas. So we have to make sure that the format is pandas. So we have to convert the format into pandas format, datetime format. Okay, so you have you just follow this one is the date equals panda to datetime. Okay, datetime data date, I think so, and a format. So I'm trying right now to convert this into a pandas data frame so that it will be readable. Y and M and D. Okay, so don't worry because it is not quite important, but you will see this code every time you have when you are seeing the production data and you have to convert it into Python. You have to make sure that it fits to the format. And if we print the data, okay. Okay, so I think there is, okay, so format here, it is not brackets, but here. Yep, we have this data already converted into datetime format. Okay, but yeah, the important thing is we will calculate the aquifer influx in 8 minutes. Okay, so we copy all the inputs. Okay, we copy all the inputs. Oh, okay, so okay, so for the input, okay, so we have to calculate first the aquifer constant. Okay, here. Okay, the aquifer constant, we have to calculate first the aquifer constant. So we have already list down all the required inputs here. Kilometers. So our R is the reservoir extent. Okay, for this, so it will convert into feet because it is originally from kilometer, and H is in feet. CF is okay, so CF is okay, so we have already defined CF first, so we don't have to define it again, and the porosity is 0.2. Okay, so if we okay, so we again type our function. Okay, so B star is the aquifer constant. Y calculate aquifer constant, I think is right. Our error, I have to see in this detail, aquifer constant. Okay, and if we print the result, okay, this one is the aquifer constant. Okay, so the aquifer constant, it has the unit of, so aquifer constant. Okay, so if you want to print the result, you can print like this, B star. Okay, and it has the unit of reservoir barrels over D day and PSI. Okay, so this one is our result, and from this aquifer constant, okay, we will calculate the aquifer influx. Okay, and we are going again to this detail. To calculate aquifer influx, it needs daytime pressure, CF permeability. Okay, so we will copy it again. Okay, so we'll just sort out all the variables that we have already defined and which one we haven't defined before. Okay. For the daytime, we have already defined, so we just delete it. CF, okay. CW, we have already defined first. And there is a new variable here, which is the permeability. The permeability is 105, okay. The porosity, okay, so we have already defined, so we don't have to define it again. The water viscosity, okay, so water viscosity is 0.3. Okay, this one, the reservoir extent, we have already defined, so we don't have to define again. And the B star is the aquifer constant. So we've already calculated the aquifer constant here, okay? So we just pass the equals B star, okay? We have done with our variable inputs. Now we will calculate our final aquifer influx, okay? So for the aquifer influx, it needs this one. So okay, so I think, okay, so aquifer influx. I think this one, this variable, you can type any name, aquifer influx, or A or B. Okay, so I would call it WE. Y, okay, y dot calculate aquifer. Okay, the way we define here is just the way we defined before, like y, okay, or x. This one is, so we just write down daytime pressure, CF, CW, CF, sorry, permeability, porosity. Okay, this one, RR and B star. Okay, and it will print us the aquifer influx. Daytime is now defined, okay, because, okay, so because we haven't already defined daytime, daytime is this one, okay, daytime. So data, so if you are, maybe you have any question to use yesterday, and I have already added a new notebook in the WhatsApp group. You may learn, okay, and then we have already defined the daytime. We will have, okay, the daytime data date. It has no variable. Okay, so I think data date. Data date has no variable. Okay, so just take, okay, data date has no variable. Data date. Okay, this one is our aquifer influx result. Okay, and after this, always when we have something, we have to plot it. Okay, so this is we just plot. Okay, we plot all the data. The first one, so I want to plot. It's like this way. If I have any okay, so I don't have the image. So daytime. So because daytime is the time, right? Daytime. Okay. Okay, so I want to plot the aquifer influx versus the daytime. Okay. So this one is our aquifer influx. Okay. So that's it. So we have already know the aquifer influx here from the start of production to the end of production. Okay. So maybe for the final touching, we can make a title like aquifer influx, okay, from the name of the field. This is called the fall field of fall field with size 20. And I want to change the size. Okay, change the size to okay, this one. Okay, for label, date or time, date, MPLT, Y label, aquifer influx, and it has the unit as barrel. Okay, barrels. And then we show the plot. Okay, so we show the plot. So we are quite finished here. So this one is this one is a, okay. Okay. Okay, I've just been disconnected. So we have actually finished everything. So yeah, so finally we have already seen here. Okay, so this one, so we have already finished all things. Okay, so from this tutorial, I've already explained how to plot the material. You can use this library for your research or for your study. And basically, some of the participants, I'm seeing the chat box that maybe this is quite fast, and we should have more time to add some session on basic with Python, because last week we haven't already covered that. So I highly suggest that you can go to the notebook that I have it is called the very brief intro with you can find all the codes you can learn from there, because actually the way I explain right now it is to the way I show it in the notebook for the brief intro.
Johannes,
so if
are you there?
already understand the brief intro, and you can, because Python requires. Hello?
Yeah,
Destiny?
Johannes, are you there? Yeah.
Yeah, I'm here.
I think you were breaking. So or maybe it's maybe it's I think you.
Yeah.
Hello? Can you hear me?
Yes, Destiny. Yeah. Yeah, I can hear you. Okay, so do you hear me, Destiny? So I'm about to close this tutorial. So if anyone has want to learn Python, you can go to the notebook that I have shared in the WhatsApp. But thank you all for your participants in this tutorial. If you want to ask for anything, you can just poke me directly. Okay, so yeah, so I will see you
Yeah.
next week when we'll explain about well test analysis. Okay, so
Wow.
have a good day all and stay safe.
Wow.
And
Thank you
I'll
so
see you
much,
next week.
Johannes.
Thank you so
Thank
much,
you so
Destiny.
much, Johannes. Yeah,
Yeah.
it's a wonder. It was really a wonderful section. Mr. F. Peluso says big thanks and big please send your notebook. This was really fast. And Mr. Yusuf Fataya, they
Sure. Yeah,
says
yeah. Sure.
thank you for this wonderful
Of course.
training, Johannes. Mr.
Sure.
Francis says thanks. Jason Gendo says thanks. And Miguel Gonzalez says thanks. And Chimwaya Ibechiozo says thanks for today. Please send the notebook. And then Rodrigo says thank you. So thank you very much, Johannes, for this wonderful section. It was really, really amazing. And and then we are also hoping that you guys will join us next week for the well testing section. It's even going to be more amazing. So remember, I will send the assignments and we'll send all necessary information you need. Please remember to do your assignment and upload. If you're having any question, as Johannes have said, you could chat him up, or you chat me up, or you chat up any of the admins, and we'll be there to help. Thank you very much, guys, for participating in this course. And thank you, Johannes, for wowing us. Thank you for that.
Thanks, Destiny. It's our pleasure too. Yeah.
That amazing, a unique way of explaining and breaking down things. And it just simplifying everything just makes everyone comfortable. Thank you for that.
Sure.
So
thank you, guys. Thank you, Destiny.
You're welcome.
Yeah.
So see you next week. Yeah.
See you next week, guys. And thanks, Destiny. Have a good day and good weekend. Okay. So stay safe, everyone. Thanks for your participation. We'll see you next week.